Hi guys, let's solve today's Leetcode problem, which is problem number 153. Find minimum in rotated sorted array. It's a medium problem. Suppose an array of length n sorted in ascending order is rotated between 1 to n times. For example, the array this might become this if it was rotated 4 times. Okay, so after rotation it is like 0, 1, 2, and the rest of the elements are rotated. Okay, and it is like this if it is so rotated 7 times, which means length was also 7, and after rotating it exactly 7 times it became the same. Notice that rotating the array something like this one time results something like this. So this is the elements, and the last element from here comes to the starting. So the same happen. This is here. Given the sorted array nums of unique elements, okay, return the minimum element of this array. You have to return the minimum elements of this array. You must write an algorithm that runs in O of log n time. Okay, so there is few things to notice. One is that we have to write this in log n time. All elements are unique and it is rotated between 1 to n times only. Okay, so this is few things to note. I'll come to that later. Now let's see this example. So in this, if you see, this array is rotated 3 times, and so 3 elements are present first. And since this is sorted and then rotated, so this is the minimum. Okay, one is the answer. If we see the constraint, so n is a small value, so normal brute force approach will also work here, but question itself states that you have to write it in log n. Okay, now approach that we are going to cover is one is brute force and the optimal. Now let's see. So brute force is nothing but linear search, and I mean here we don't for us it doesn't matter whether array is sorted, rotated, or whatever. The question is just to find the minimum. I mean, simply we can apply linear search. So we have to find the minimum value. We start iterating in this direction. We'll see first value. Is it minimum than our current? So initially we initialized with into max. Yes, it is less. So we'll mark it 3. 4 it is less, no. 5 it is less, no. Now we came to 1. Is it less than 3? Yes, it is. Now when we came to 2, it is not, and then we reach the end of the array. So at the end we find the value minimum 1 as the our answer. So this is straightforward linear search approach. And if you see the code for this, so here same thing we have did. We initialize the nums dot size, the minimum value we have taken as into max. We are iterating over the array and we are calculating this minimum value, which is minimum of minimum comma nums of I, and at the end we are returning the minimum. So this is just the minimum finding that we have did, and time complexity for this is O of n since we are iterating over the array, and space complexity is O of 1 since we are not using anything extra. Now um, so the key things to notice in the question, that one was that array is sorted, okay, in ascending order, so, and it is rotated. So whenever it is given sorted, we can definitely apply binary search over here, and it is rotated 1 to n times. Okay, so sorted tells us binary search. Okay, and it is rotated 1 to n times, but uh, it can, I mean, in some other question it can be something greater than n times also. So if it is greater than n times, we should know that we have to apply modulo. Okay, if it is greater than n times. If not, then we are good. In this example we are good. I mean, this is particular question we don't have to do anything. Now unique elements. So normally when we apply binary search, right, so let's say there is something like 1 2 2 2 2 3, something like that. Based on some condition, we whether so our low pointer was something here, high was something here, and we are on some mid pointer over here, and based on some constraint. Okay, in general binary search is based on some constraint. We will either choose to move left or right side of the array. Okay, so but since is it and if there is duplicate, since in this example there is duplicate, so we need to handle duplicate also. But the question here, it says it's unique element, so we don't have to worry about that also. So yeah, that's all, and let's see how we will apply binary search. Now for binary search, main idea is to locate the rotation point, and because the minimum element is exactly where the rotation happens. Okay, so for example, here if you see, this array was originally sorted, right, and then rotated, and it rotated at 0. Okay, so 0 is our rotation point and also the minimum element if you see. So notice the array is divided into two parts. Okay, two sorted parts. One is this left sorted part and another is this right sorted part. Okay, both of these parts are sorted, and the right sorted part always contains the rotation point. Okay, this right sorted part will always contain the rotation point and therefore the minimum value also. Now the question is how to determine whether our mid lie in left sorted part or right sorted part. Okay, so we have to determine that. Okay, and key thing is that our answer will always lie in the right sorted part. Okay, and why it will be, because this is rotated, right? So after rotation the higher elements whatever were here came here, right? So it was originally sorted and then rotated, so higher elements move to this side, right? So whenever it moved to this side, so I know that left sorted part will be always maximum and right sorted part will have this rotation point, which holds the minimum value. Okay, so our answer lies in the right sorted part. Now, normally in binary search, we have this low pointer and this high pointer, and then we have this mid. Okay, so we normally have to find where does our mid lie. So when we are calculating where does our mid lie, does it lie in the left sorted or it lie in the right sorted? Okay, right sorted. So we have to find that. For that, what we can do is we can simply compare this nums of this mid value. So what we can do, we can compare nums of mid with nums of high, and we use nums of high because the high pointer always lie inside the right sorted portion. Okay, so this will always lie in the right sorted portion, which and right sorted portion contains the minimum value. So if nums of mid, this value is greater than nums of high, then if the so which means that middle element is greater than the last element. Okay, if that is the case, it means that mid is in the left sorted part. This mid lies in this left sorted part, and that is true, right? This mid lies here in the left sorted part. So in this example, if you see, the 7 is greater than 2 and it lies in the left sorted part. That means the rotation point and the minimum element cannot be on the left side. Okay, our mid, here it is, and our rotation and the minimum value, rotation point and the minimum value cannot lie in this part. So we have to explore this right sorted half. Okay, so to explore, this will definitely lie here. To explore right sorted half, we move our low pointer to mid plus 1. Okay, so now our low pointer will point over here. We moved this low pointer. Now other case is if nums of mid, this value, here we will again calculate mid value. Okay, so low is this, high is this, mid will be somewhere here. Now, if this mid value is less than or equal to high, okay, in that case, this middle element is lesser or equal to this high, which means that mid lies in the right sorted part. And if you see also, right, so this mid value, so it lies in the right sorted part. So 1 is less than equal to 2, and it is in the right portion. Okay, so since the portion contains the rotation point, so mid itself could be the minimum. Okay, and this itself can be one of the minimum answer, so we cannot discard mid. Instead, what we will do, we will keep it in the sorted search space. Okay, and we will move this high value to this mid only. Okay, so our high will also point here after this. So now we are left with 0 and 1. So what we will do, again we will calculate this mid. So mid calculation will give us what was this indexes, 0 1 2 3 4 5 6. So 4 plus 5 by 2 will give us 4. Okay, so our mid also lies here, new mid. Okay, so our new mid lies here, low is here, and high is here. Now again we will do the comparison, and mid is again less than or equal to high, which is 0, is less than 1. So again our mid is lying in this sorted part. So what we can do, we can again move this right high value to mid. So high will also point here. Okay. So now if you see, low and high both are pointing to the same variable, which means we have found our rotation point, hence the minimum value. Okay. So the idea is very simple. If nums of mid is we are here, and here somewhere our mid is there, this is low and high, and if this nums of mid is greater than nums of high, which means mid is in the left sorted part. This mid belongs to this left sorted part. Our array was clearly divided into two sorted parts, right? If this is the case, which means our mid belongs to the left sorted part. So if that is the case, the rotation point was on the right side. So we moved our low pointer to mid plus 1. Okay. Otherwise, if mid is in the right sorted part, so the rotation point is at mid or somewhere in the left. Okay. If it is at the left sorted part, then in this example, here our low is there, high is there, and if our mid is here, right? So our answer would lie somewhere in this left sorted part or exactly at this value mid. So in that case, what we can do, we can move our this high pointer to mid. Okay. So and when like last at last low was equal to high, that index point to the rotation point, which is our minimum element. So that is the simple case. Now let's see the code for this. So here we have this few pointers, low, high, and where it is nums dot size minus 1, and we are having this check if low is less than high. Okay, because if we reach the equal case, which means we have found our rotation point and hence the minimum, so we will break over there. Okay, if low is less than high, then only we will keep on calculating. So we have this mid value calculated as low plus high minus low by 2. Now I'll explain why I did that. Normally we do it as low plus high by 2, right, to get the minimum value. But if this in our example, in our this problem, these values are high, is constraint is really less, but in general it won't be. Okay, so for that reason, if we add these two higher values, so it all together can go out of integer out of bound. Okay, so maximum value what integer can store, this can go greater than that, and which will give me altogether wrong answer for wrong index for this value. So for that reason, to avoid integer overflow, we write it as low plus high minus low by 2. Okay, now if we open this bracket, so it will be 2 times low plus high minus low by 2. Okay, and if we do this calculation again, so it will come same as like this. So this is 2 times low, 2 times low, so it will only become 1 time low and high by 2. So and if we are doing low minus high by 2, so this will be never greater than max integer value. So we are within our integer bounds. So for that reason, we always do in binary search, we always do mid calculation like this. Okay, now we are checking this case, nums of mid is greater than nums of high or not. If it is, which means this mid belongs to the left sorted part, and our maximum value or the rotation point belongs is in the right sorted part, so we'll move our low pointer to mid plus 1. Otherwise our answer lie in the left sorted part, or it can be at the mid also. So that is why we pointed a high to mid value. Okay, so at the end when we find everything, our at the end nums of low will be holding the uh, um, lowest value or the minimum value. Okay, so we can return that. Now there is one more observation that we can make, that let's say when we were calculating, okay, so this was low, this was mid, this was high. Now let's say when we started our calculation, at that point itself, this low nums of low is less than nums of high. What does this mean? This means that this part is sorted, and when we this part is already sorted, we know that minimum will lie over here. Then why do we need to really calculate further? I mean, do any operation further? We don't need to do, right? So in any part when we are exploring, we can compare if nums of low is less than nums of high, which means this is already sorted. And if it is already sorted, minimum will always belong to the nums of low point. So we can directly return it. So doing this will save us with some further more operations. So this is the further optimization on top of this. So we will write it as if nums of low is less than nums of high, then in that case we can directly return nums of low. Okay. So yeah, that's all for this approach. And if we discuss the time complexity, so every time we are discarding the one half and then exploring the other one, and then also discarding the other half. So for that reason, the time complexity for this binary search in general is log of n. Okay. So, and space complexity, since we have taken some few variables only, so it is O of 1. So yeah, that's all for this approach. I hope you like this video. Thank you for watching. Stay tuned for next videos.